This is Dr. Carroll, and this video is about external sorting. Now, selection sort, insertion sort, bubble sort, cell sort, heap sort, merge sort, quick sort, bucket sort, radix sort, they all assume that the contents of what you're trying to sort, the array or arrays, is the case, for example, in merge sort, can all fit into main memory. But what if the data is so large that it can't fit into main memory? That's when things get interesting. Okay, well, let's back up a minute. Let's assume you have a 2 gigahertz processor. That means it can perform 2 times 10 to the 9th cycles or instructions per second. And that's a simplification. Take a good operating systems class. Okay, and for main memory, access times are currently measured in nanoseconds. However, for a hard drive, 10 milliseconds is close to typical. So, for a seek time of 10 milliseconds, that means it takes 10 milliseconds to find the first byte. Okay, and in 10 milliseconds, how many instructions could we execute? We could execute 20 million instructions in the time it's going to take to find that first byte of memory. Now, truth in advertising, once you find the first byte, it takes very little time to get the rest of a block in, but that first byte takes a long time on a spinning disk. Now, worse yet, what if your data is so large that it's actually written to a tape drive, using a tape drive? It would have to physically wind the tape, the meters and meters of tape, to be able to find the correct location. So let's give an example. Assume you're using quick sort and you're trying to find the median to choose a pivot. You're trying to find the median of the first, the middle, and the last elements in a large data set. This will require 3 disk accesses, or even worse, if it's on tape, you'd have to read the first one, advance it to read the middle one, and then advance it even more to read the last one, and then rewind it. That takes a long time in comparison to how many instructions can be executed. So we need to do things differently. Let me show you a demo just to solidify this. So here, this is just in Bash, I'm gonna loop through 1,000, 10,000, up to 100 million of random inputs, and I'm gonna run them with quick sort, okay? So let's look and see what we have. Okay, so reading in the values, opening the file, reading them, assigning to a dynamically allocated array, and then closing the file, that takes half a second. Whereas quick sort takes a 1/12 of a second. And then now for a 10,000, it's about 10 times larger. It takes 5 milliseconds. Sorry, this is 0.5 milliseconds. And it's not even a millisecond to perform quick sort. Let's jump down to 10 million here. 10 million, it takes 6 seconds to read in the values, and it takes 1.7 seconds for quick sort to perform its operations. But except reading values is order n, and quick sort is what? Average case, because these are random values, n log n. But that's comparing apples and oranges, because we're comparing instructions on the CPU compared to I/O times, and so you can already start to see the wide differences in that. And this is fitting into main memory even. And so, 100 million we got to wait on. We can peek up here. It took 41 seconds to read it in, and almost 15 to perform quick sort. So there's a huge difference there between the two. Okay. Now let's see a simple algorithm to perform an external sort that takes into mind that these accesses to disk or tape take a long time. And we're going to use 4 tapes in this example. You can get away with 3, but it's a lot easier to show with 2. Okay. So in summary, we're going to read in X items, where X is the maximum number of elements that are going to fit into memory. And we're going to sort them in memory, and then we're going to write them back to the tape. And then we're going to merge 2 groups of X items and write them to tape. And then we're going to merge two groups of 2 times X items and write them to tape. Now, merging, we're just going to use the merge from the merge sort routine. And it works really well for tape because a tape gets the right spot, and then it just, once it's there, it doesn't have to seek anymore. It's very quick to read in contents once you're in the right location. So to get to the beginning of someplace, even if it's 2 times what will fit in memory, it just reads it. And since we're saying we have 4 tapes here, we'll just have 2 tapes going on the merge at a time. It just reads, advances it just a little bit, advances it, reads it, advance, and moves down that way. Okay, and so that's going to be really efficient for tapes as far as tapes go. And then we're going to repeat this until all the items are merged. So let's see this in 8 steps to make it a little bit more concrete. We're going to read X items in, X being the maximum number that's going to fit into main memory. We're going to sort them in memory because that's really fast in comparison to the time it took to read them. And then we're going to write them back out to tape because we can only fit X items at a time in main memory. We're going to repeat these steps 1 through 3 until all the items are read. And we're going to alternate between writing them from tapes 3 and 4. Okay, so we'll write X items to tape 3 and then X items to tape 4. We're going to rewind all the tapes. That takes a little while. And then we're going to read X items from tape 3 and tape 4. Read X items from tape 3 and read X items from tape 4 and merge them onto tape 1, or we'll alternate with tape 2. And then we're going to read in 2 X items from tape 1 and 2 X items from tape 2 and merge them either to tape 3 or tape 4 as the case may be, so that we can read from 2, write to 1. Then we're going to repeat items 6 and 7 until the total number of items are read, and we'll do this by powers of 2 because it just gets larger and larger and larger. Okay, and so that's a simple algorithm. Of course, there's much more complex algorithms. The field of research when you're trying to sort large numbers of items or a large number of items that have a large memory footprint each. Let's see an example. Here we have a number of numbers, and we're going to assume that they're all on one tape, and then we're going to execute this simple algorithm here. Here I'm going to have X equals 4. I know that's not how it works in the real world, but it'll just be simpler, and I didn't want to bring up 10 billion numbers and fit them into my Emacs window. I'm also going to use the notation here that the vertical bar is going to indicate the read-write head location on each tape. So if we have tape 1 here, and I've blocked them to show that X equals 4 here, we can read in this group, and then this group, and then this group, and then we can read in this group, okay? And that's how much we're saying for this simple example fits into memory. And notice all the read-write locations for the tapes are all at the beginning of the tape, okay? So first we read in from tape 1, and we're going to write it out to tape 3 here. So we read it in, we sort it in memory, and then we write it out, and we leave the read-write location after that. Okay, we're going to repeat this, and for the next group, we did that for this group. Notice this advanced here. We're going to read it for this group, and then we're going to write that to tape 4 location. So we've read in this group, we've advanced the read-write position, and now we've written this out to tape 4. We're going to repeat that because we're going to do that for this group, and we're going to write that to tape 3, and it's sorted, and we're going to do that small group here at 95 and 12, and we're going to write that out to tape 4. Okay, and so that's the first step. Is now they're all sorted. Now what we can do is do a series of merges, and that's going to go quickly. But first we have to rewind all the tapes. Okay, rewind all the tapes, make sure the markers are here. Well, we rewind all the tapes that we use. Now we're going to read one group from tape 3 and a group from tape 4, and we're just going to walk down it and merge these values in order as we learned about with merge sort. We're going to write that to tape 1, and that's going to take up 2x amount of data, and then we're going to leave the read-write head here at the end of that. Now we're going to alternate. We're going to take these two groups, and we're going to write them to tape 2 here. You guessed it, we got to rewind all the tapes, and you'll notice I've ignored the data that was there. It's because we rewound it, and it's going to be accessible for the future, and we really don't care what was there. It is there still, but we're just going to write over it. Okay, so now we're going to read in this 2x block from tape 3, and this greater than x, but actually smaller than 2x. These two groups from tapes 1 and 2, and we're going to write them out to tape 3, and that's shown here. Now we may need to copy all of the items from tape 3 back to tape 1, just depending on how things work out. Okay, now that was a simple example. Now imagine applying the same algorithm to 10 billion records, where each record is a megabyte. Of course, X is going to be much larger to fit the main memory. Okay? Now let's talk about efficiency. For external sorts, efficiency is measured by the number of I/O transactions to or from disk. So how many blocks were written to and from disk, and that's really how we're going to measure it. And so when comparing algorithms for external sorts, you would the overriding factor is how many times did we have to access disk, read to it, or write from it. And that concludes today's video about external sorting.